Hello everybody, I hope you're all well and staying safe. My name is Phil Prosser. I'm a domain solution architect here at Red Hat. I focus on our Red Hat runtime technologies and our integration technologies, and today I'm here to talk to you about Quarkus and why Quarkus is making Java awesome again. Now, if we were all in the room together, you may know that 25 years ago Java was born, and so it is its 25th anniversary this year, so we'd all get up and we'd all sing happy birthday to Java. Of course, we're not all in the same room together, which is probably fortunate for us all, basically, because you don't want to hear me singing, that's for sure. However, that 25 years has meant that Java has been very successful over that time and is very pervasive in everything that we do. There's probably very few of us that go a day where we're not dealing with or interacting with something written in Java somewhere in our sort of daily lives. So it's out there and it's massive. My particular interest in Java is using it in the enterprise, and in the enterprise it's also been very successful, and we see many businesses that have written many millions of lines of code of Java in the applications that they use every day, all of the time. That means investment in application, and it means investment in skills as well. So many organizations have a large investment in developer skills, architecture skills, and everything else that goes along with Java. And so it still is a very important platform. Even when we look today to new things that people are using, new bleeding edge applications that people use, maybe not so bleeding edge these days, but even things like Kafka are written in Java. So Kafka, being one of the hot topics of the moment, still has Java at its core. So it's still a really big product that people are using and consuming. However, Java needs to continue to evolve. We're all looking at different architectures and different platforms to deploy our applications on these days. And so we think cloud native in terms of the way we look at our applications. We think microservices in the type of architecture we use. Many people I talk to are starting to think serverless and event-driven architectures as well. And then from a platform perspective, people are thinking Kubernetes, Istio, Knative, those type of things. And also, of course, hyperscalers as the platform to actually deploy on. And so based on where Java's come from, to be able to support these types of new paradigms and platforms, we need to sort of keep evolving Java. And of course it has done. So over the years, Java has changed and has evolved and continues to do so. And so in particular, around microservices, cloud native and sort of cloud deployments, two frameworks have come up, which are microprofile and Spring Boot, which are probably the two most popular ones. And what I want to do is just take a couple of minutes here just to talk briefly about microprofile and what it is. And it's something that's important to me, and it's something that's important to us here at Red Hat as well. So microprofile, firstly, I've got a slide coming up next, actually, which will talk about what it isn't, but it isn't Jakarta EE. It isn't JEE. Microprofile is an Eclipse community-based project whereby many sort of vendors get together and develop an implementation that is basically based around API. So it's looking at how do I sort of build APIs in Java, how do I expose those APIs in Java, how do I then integrate them into sort of health and metrics at runtime, how do I look at things like circuit breaking, for example, defining my interfaces, and then even going up to doing things like tracing. So I guess the point is it's very focused around what we need in terms of cloud native and microservices development, and not focused on that big monolithic type of approach that we would have used in the past. So really that just brings me on to my next slide, which is really talking about what microprofile isn't. And there is a perception still that microprofile is JEE or Jakarta EE. Well, I'm here to say that it is not. It doesn't need an application server to work. It goes way beyond the work that goes on in Jakarta EE. But of course, it does feed back into Jakarta EE in the end. It doesn't require an application server such as JBoss EAP to execute, albeit we can still use our same skills, which is a big benefit of it. And then, of course, you don't need to be an existing application server customer to consume it. So from that point of view, it's really easy to pick up. Now, the other thing that it often gets talked about in is that it's a monolithic architecture. Again, it's not. out of those things that I had on the previous slide, I'm basically choosing a set of dependencies, and those dependencies are what actually gets deployed. It does not deploy the whole of microprofile. It only deploys what I need. And then the other thing is as well, it is a very fast moving project. It's not a standard. It is a community that develops this. And we've had actually 8 releases of microprofile in the last 24 months. And so it's a fast moving, very innovative project that is sort of looked after and contributed to by multiple different vendors, and of course Red Hat being one of those. So it's taking the brains from many different organizations and producing this microprofile standard. So we do have microprofile for microservices and cloud native, and we also have Spring Boot for that as well. So it would seem to be that I'm here trying to tell you something about a problem that's already been solved. So what am I here to talk about? So clearly there is something that is still amiss when we think about those architectures and what we actually want to do. And that's what I'm really here to talk about and see if we can address that issue. And so to do that, I want to just take a little look back over history and how we used to deploy applications in Java to sort of where we want to go today. Within the back of my mind, I'm looking at cloud native, I'm looking at microservices, I'm looking at serverless in terms of architecture, and event driven in terms of architecture, and always having one eye on the amount of CPU and memory that those things consume. And that's really the problem that I'm trying to address. So when I look at the historical application, basically that used to be a monolithic application whereby all of the code with its presentation logic, business logic, data access logic was all munged together into one sort of application. That application would live for months. It would not get changed very often, and probably then run for a very long time in any one go. What we would also do is we would deploy multiple applications onto that same application server, and those applications might actually be doing different things. And this was in the day, take yourself back to when physical machines were the thing. We used to deploy onto physical machines whereby that application server could have all of its memory, all of its CPU processing power, and so on. There was never any worry about other things wanting to share that environment. So this thing was really designed to use loads and loads of gigabytes of memory, use lots of CPU. Nobody really cared about how long it took to start up, because once it started, it ran for a very long time. What I would then do is deploy my applications into it and also redeploy my applications into it, hence the very dynamic nature of these application frameworks. So this sort of historical stack doesn't really suit what it is that we're trying to do in the new world and the new architectures that we're looking to deploy. And so that moved us on to microprofile, Spring Boot, and those type of environments. But when we actually look at those, they also struggle from a very similar problem. And so in terms of the application, we are now deploying in services, and I will deploy one application onto my framework. Typically that life cycle for that application may be days, so maybe making much more frequent changes to it and updating it more often and redeploying it more often. But it still takes up hundreds of megabytes of memory and still has a large startup time. And that is because the key layers here, being the framework, the application servers, and the JVM, haven't really changed a great deal. And so when I look to deploy into things like serverless, when I look to deploy to cloud, when I look to deploy to things like Kubernetes platforms, well, that's actually doing is either costing me a lot more money because I need lots of memory and lots of startup time in the case of things like serverless. If I'm looking to platforms like Kubernetes, then I'm thinking about density of deployment. It really impacts my density of deployment when these things take up a lot of memory and a lot of CPU cycles to do that. And so what we're trying to do with Quarkus is really think about how can I start to address these type of issues. And so that sort of just brings us on to the sort of the conclusion here, in that if I want to deploy cloud native type applications, then I cannot deploy as in a such scalable way that I could with Node.js, or a higher density way that I could with Node.js. And I certainly can't do the same thing with Go. And so what we see is enterprises faced with this dilemma really of sort of looking at changing frameworks and looking at changing languages that they're using into these new deployment platforms. And to a degree, that's okay. but that comes at massive expense with all of those millions of lines of code in Java that already exist and all of those existing skills that people have. So what we sort of did, and some time ago, was really to sort of take a look at this and think, well, isn't it time that somebody came up with a new Java stack that was specifically designed for cloud native workloads and for serverless type of workloads? And that's exactly where Quarkus was born, basically. So Quarkus is really trying to change the way we think about running applications in those typical environments, but arguably not trying to change the skills that we need to deploy there. So trying to get the best of both worlds: low memory usage, quick startup time, but same skills. And that's the sort of thing that we're trying to get to. So when we look at Quarkus at high level, these are the things that we're looking at, and these are the things that it does really well. So it is designed to run in containers, and it's designed to run on serverless workloads in things like Azure and things like AWS using Lambda maybe. It is designed to run on a traditional hotspot Java virtual machine, and equally it's designed to run on Graal VM. And Red Hat now has a downstream version of Graal VM, which is called Mandrill. And really the key thing here was to get to a point where Java would start up very quickly and require a very low amount of memory. And that becomes really important when we think about serverless type applications in the hyperscalers. We get charged by the amount of time my service executes. So if my service executes, the startup time is 4 or 5 seconds, and then it takes a few milliseconds to actually do its work, I'm charged 4 plus those few milliseconds. And of course, there are things you can do to have warm serverless and that type of stuff, but that's just costing more money. So what if I could get my Java down into millisecond startup time? And what if I can get my memory down into even tens of megabytes of memory instead of hundreds of megabytes of memory? That's going to represent a massive saving in terms of money, but equally a massive improvement in the terms of availability, scalability, reliability, and skills that I actually need to deploy that. We also then look at Quarkus and think, how can I make life easy for developers? So even though Quarkus has a very fast startup time, which we'll talk about shortly, the process of development and writing code and packaging it and then testing it, that whole sort of life cycle is a pain where I have to write something, package it and run it. Even though running doesn't take very long, my train of thought is often lost. And so with Quarkus, I can literally run my application once in what we call development mode, and I can make as many changes as I want. I can make changes to Java classes, I can add Java classes, I can change property files, I can do all of that stuff on the fly, and immediately those changes happen in my runtime. So from a development point of view, it makes it really easy to use. But equally, and I'll show this in just a second, those developers are still using APIs and technologies that they're familiar with. So that's cool as well. The other thing that we do as well, which works nicely in the world of serverless with Knative and also the hyperscalers, is moving very much to a reactive and imperative mode of running these things. And so Quarkus supports both imperative development, which is used by the likes of old people like me, and the more modern architectures would be using reactive programming, and Quarkus does it all, and you can mix these things together as well. And then one of the really powerful things about Quarkus is something that we call extensions. So extensions are really how we then plug in capability into the core Quarkus engine. So I talked briefly about microprofile earlier and our support for microprofile with Quarkus. But what we also have is this big ecosystem of extensions that we can actually use. So sure, I can build microprofile, but equally, if I want to start using things like Vertex, or I want to integrate directly into OpenShift, or I want to do streaming with Kafka, for example, I just use the right extension. And an extension is literally just a dependency that I put into my Maven POM. So it's really easy to consume this stuff. And these are all technologies that people are typically familiar with. So we're not sort of changing the world as such with this, but we're changing the underlying framework for sort of memory and CPU reasons more than anything. And so what I want to do is just sort of bring you some results really of the sort of work that we've done in terms of how fast it can be to start up, time and how little memory we can actually use. So let's start with startup time. So here's a slide, and we've got two examples on here. So the stuff in grey is a traditional cloud native stack. Then we have Quarkus running in blue on the JVM, and then we have Quarkus running with the Graal virtual machine. And so for a very simple REST-based application, what we're measuring here is the time from a request is made to the time that the response comes back when that Java isn't actually executing at that point in time. And so what we're trying to do is really see what this would work like in the world of serverless, basically. So if we're using a traditional stack, just for a very simple REST Hello World service type application, the traditional stack takes 4.3 seconds to start up. By running that in the Quarkus framework on OpenJDK, that comes to below sub-second. So a 4 times improvement, basically, just from moving to Quarkus and running still on OpenJDK. If I then take my Java logic and compile it down to native code using the Graal virtual machine, then all of a sudden I'm into 16 millisecond startup time. Now that's something that I can really work with when I'm thinking about serverless type applications. I'm getting no cost basically from the start of my application. It is literally firing up, doing its work, and then shutting down again. Graal VM is to use Graal VM with Quarkus is literally inside of my Maven project, just setting a profile to native. So I say Maven package -p native, and then all of a sudden I get a native version of the application. It takes a little while to compile it down, but once it's there, and I can just literally execute it natively on my machine. When we look at a more complex example, so REST with sort of create, read, update, and delete type services, then again, we still see the same levels of performance improvement. So 9.5 seconds for a traditional framework, 2 seconds for running on a JVM, and 0.042 seconds when we actually run natively. And so these are massive savings that people are able to make in terms of startup. And it makes using technology such as OpenShift serverless, which is Knative, or using some of the hyperscaler serverless capabilities realistic with Java. And I can use my existing skills to do that. But how about on the memory side? And let's just take a look at what we're getting from memory usage. So again, we see really good results here. So this is just for time looking at the REST and CRUD service. But what we have is on a traditional stack, 209 megabytes to actually perform that workload in memory. Then literally by moving to Quarkus, that comes down, moving to Quarkus and OpenJDK, that comes down to 145 megabytes. And then when we compile down into native code using Graal VM, it becomes 28 megabytes in terms of memory consumption. So we have a lot of customers looking at this and thinking, wow, this is really good. There's a lot of higher density of deployment I can do, startup times as serverless, make Java realistic in doing those type of things as well. But don't just take my word for it. There are sort of plenty of examples out there now where customers are using Quarkus, and customers are starting to see some really good benefits from moving to Quarkus. So here we've got Go with Flow, 79% reduction in memory consumption when the application is under load. So this isn't just doing a simple request. When we're looking over here, we've got 1 minute startup times down to 400 millisecond startup time. So this is just confirming everything that our tests have been showing. 6.7 second startup time and down to 10 millisecond startup time using Lambdas on AWS. Again, that's really good, really impressive stuff. So Quarkus is really going to help people save a lot of money and a lot of memory, going to save a lot of money on memory and CPU consumption when using cloud type applications with Java and with Quarkus, but of course keeping those existing skills in place. So what this all means is that with Quarkus, all of a sudden, if I was to run Quarkus on a JVM, I'm sort of comparable now to using Node.js as a runtime in terms of density of deployment. And if I was to compile down to native code, then all of a sudden Java also becomes comparable with running Go code as well. And the key important thing here for me is that those skills that I'm using to write my Quarkus applications are the same skills that I'm using to write my EAP applications, using to write my Spring Boot applications as well. And I can just move those skills across and get those advantages using the Quarkus framework. And of course, what I can also do is move my code across. So I can hear you all asking, well, how does this work? How does all of that saving come about? So let's just spend a couple of minutes looking at very high level what we're actually doing and why we are different to the traditional methods of the dynamic frameworks. And so when we actually look at a dynamic framework, it actually, when you think about it, it all becomes quite straightforward and simple, albeit extremely complicated to write. When we actually look at a standard framework, what it does, build time, so the developer will basically package an application. So they get a jar file, a WAR file, or whatever it may be, jar files if we're thinking Spring Boot or microprofile. What then happens is we put that into a runtime environment, and that runtime environment, of course, is the jar file because it's typically an Uber jar. So I execute that jar file. And what happens then is almost unbelievable in terms of what we want from a microservices type application. Because of the dynamicness of that framework, everything now happens to make that application executable at runtime. So it loads things like the configuration files. It then looks at those and parses those and works out what it needs to do. It looks at things like all the annotations that we may have put from a CDI perspective into my application, and possibly then goes through doing lots of Java bytecode injection. It then builds up this complete model of what pulls what and understands how everything hangs together so it can execute. And eventually it starts up all the management ports and gets everything executing. Now, that takes a long time to actually execute. Actually puts a lot of code into memory as well that never gets taken out of memory until that JVM goes away. And so when we think about that in the context of a dynamic application framework, sure, it's really important it does that, because applications are going to be deployed often, or not so often, I mean, but more applications are going to be deployed. I may need to redeploy my application as well into runtime. And so, of course, when it redeploys, it needs to go through all of these things, working out how to execute that. But we're thinking about running as containers, which are immutable. We're thinking of running as serverless, where the function executes, it does whatever it needs, and then it goes away. So this concept of dynamic frameworks and long time to load things and long times to start things doesn't matter. We don't need it. So what if I can move most of this stuff that happens at runtime into build time instead? And that's sort of exactly where Quarkus is coming from. So what it wants to do is to move all of that work that happens at startup into build time. And so from reading the configurations to building its view of the world to actually packaging and then potentially packaging down to native code as well. And one of the things I'd like to talk to you about another time is actually what happens at that point. But even if we build down to hotspot, what we're basically doing is all of the work that starts at runtime, we're now doing that at build time. So all of those Java classes that were required, all of that time that's required to do that work just goes away. And that's largely how you see the memory and CPU saving when we actually execute on OpenJDK. The other step is then to package down to native code. So if we go all the way to native code, then the Graal VM takes it a step further. It now goes through all of the Java classes that are in my application, all of the Java classes that I'm consuming from the JVM, and that is what actually gets deployed at runtime. So I don't get a full JVM in effect. I only get the classes from my application that I need, and I only get the classes from the JVM that I need at execution time. And that's simply how native execution is so much faster and so much lighter weight in terms of the memory requirement that it actually needs. So in runtime, all of a sudden, all I really need to do is my management pieces. I just need to open up, all the ports need to be opened, and I start executing. It has to do nothing, basically, to actually get executing. And that's why, to some degree, it's almost an unfair comparison when comparing Quarkus against traditional dynamic application frameworks. But this is the new way of working, and this should be the way people look to deploy Java on sort of serverless and cloud native types of environment, really. And so just quickly on the extensions, the way this actually works is the extensions that are built have two parts to them. They have a deployment time, a runtime, I beg your pardon, and they have a build time part to that particular extension. At build time, it will load the build time part that allows me to actually do the packaging of the application. Then at runtime, it only loads what it needs to execute at runtime. It does not load the whole of the extension at runtime, again, allowing me to slim these things down. At dev time, so I mentioned earlier that I've got live coding. Live coding basically loads both. So it loads build time and it loads runtime at the same time. And that's what gives me as a developer the ability to change code, add Java classes, and all of those good things as I go through my development process. So I can hear you all asking now, how do I get started with this stuff? Where do I go to start using Quarkus and finding out whether it's any good for me? So there are plenty of places that you can go. The first place that I would sort of suggest is going to Quarkus.io. Quarkus.io has lots of real good information on Quarkus. It has lots of information and lots of starting guides and how do you go about deploying to Kubernetes, to OpenShift, to serverless. Lots and lots of really useful resource there. If you want to get going and start building projects with Quarkus, then there's three places that you can sort of go to do that and get started. So the first place you can go to is microprofile. So you can go to the microprofile website, choose the version of microprofile that you want to use, choose the engine that you want, or the framework that you want, I beg your pardon, the framework that you want to use as Quarkus, and then it will actually build you a scaffold project ready to go. You can also just go to the Quarkus community website. So again, you'll be able to see that when you see the slides in more detail. You can go to that and it'll actually create you a starter project there. Again, you can choose all the different dependencies you want. If I want to do things with Kafka, I can choose the Kafka extension and so on, and it will build me a skeleton project ready to go. So I can just start writing my code. If I'm a Red Hat runtimes customer, then we also have a Red Hat supported version of Quarkus. So you can actually go to that site and do effectively the same as you can with the Quarkus site. You can choose the extensions that you want, and it will then build you a scaffold project ready to go. The difference with the Red Hat version is that you're using the Red Hat binaries, which means you're entitled, assuming you've got subscriptions, you're entitled to sort of full support from Red Hat with those versions of Quarkus. So in summary, Quarkus is a really good runtime that, in my opinion, anybody doing Java should be looking at, should be considering. If I'm looking at writing new applications that have a requirement of low memory footprint and quick startup times, and if I'm using these new architectures, then everything's going to have those requirements, then I should be considering Quarkus as a potential solution for that, and potentially even compiling down to native code if required. If I have a massive investment already in Java applications that may be monolithic in nature, maybe I want to start breaking those applications apart into microservices using things like the Strangler pattern. And for those microservices that I start breaking out, then Quarkus would be an ideal runtime platform for those. If I'm looking to use Java for any form of serverless, whether that be serverless using Kubernetes type technology such as Knative, or whether that be running serverless functions on Amazon, Azure, or Google, then I really should be thinking about Quarkus for those as well. Those need super quick startup time to be any good whatsoever, and that just becomes really, really important. And as we've demonstrated, Quarkus has amazing startup times and very low memory consumption, so we'll reduce cost and increase density of deployment. And then finally, the event-driven architecture also is a really good way to think about deploying these stuff. So having event-based services that are there that are not running until an event causes them to react to that particular thing that occurred. Quarkus, again, could play a really interesting, innovative role in terms of memory consumption and those type of things in those applications as well. So I thank you for your time. Hopefully next year we'll all be able to get together in person. It'd be really good to catch up with people in person. So hopefully see you all soon. Thank you very much.